Okay, N2O, so dinitrogen monoxide. Let's look at this here. We have 2 nitrogens, each with 5 valence electrons, and 1 oxygen with 6. So we have 16 electrons to work with. All right, nitrogen is the least electronegative, so let's just put it in the middle. Doesn't matter which way you put these, which side you put these on. That won't really matter. Okay, so 2, 4, 6, 8, 10, 12, 14. Oh, 16. There we go. I was like, I'm missing some. 16. Okay. So here, this one, 1, 2, 3, 4, 5. This nitrogen has a 0. This nitrogen has a +1. This oxygen has a -1. Okay, so this is, as far as things go, probably pretty good because nitrogen is less electronegative than oxygen. So the positive is where it should be if you have to have a positive. Now let's try another one. What if we made it with the double bonds? 2, 4, 6, 8, 10, 12, 14, 16. Now the oxygen is 0 because it has 6. This nitrogen is still +1. And this nitrogen is now -1. So the +1 is still on nitrogen, which is less electronegative, but the -1 is on nitrogen, which is less electronegative than oxygen. So this is not really the best way to go. Now, what if we moved our triple bond over to the other side? And this. This is going to be all kinds of crazy. So this oxygen is +1. This nitrogen is also +1. And this nitrogen is -2. This is a terrible structure. So out of all of these, this one is the best one. Now, what about those of you who said, well, I want to put oxygen in the middle because there's only one of them? Okay, let's do that. Let's put oxygen in the middle and see how things go. So here, 2, 4, 6, 8, 10, 12, 14, 16. All right, formal charge. Oxygen is now +2. 2, 3, 4, 5, 6. This nitrogen is -1. 1, 2, 3, 4, 5, 6. This is also -1. That's absolutely terrible because oxygen is more electronegative and it has the positive charge. So that's not a good structure. Let's maneuver it another way. Let's move to single and triple bonds. All right, maybe it got a little better, maybe. This nitrogen is 0, so that's good. That was an improvement. This oxygen is still +2, that's bad. And this nitrogen is now -2. All right, so that's not really an improvement, not overall. Same thing when you switch the triple bond to the other side. We're just gonna flip the charges there. So the oxygen is still +2, this one's 0, that one becomes -2. So these 3 structures are in resonance, and these 3 structures are in resonance. But of all the possible configurations, this formula is going to be in this one the most often. Okay, let's look at here, CH4. Carbon has 4, sulfur has 6, 4 hydrogens, so we got 14. Okay, so let's see what happens There's a couple of options here as well. So let's see. Carbon should go in the middle. And then we have sulfur. And, you know, I like symmetry, so let's put 2 on each of them. Okay, so I've used 2, 4, 6, 8, 10. 12 and 14, because remember sulfur can take the expanded octet. That was kind of strange, but let's see how this works out. 1, 2, 3, 4. Carbon 0. The hydrogens are, of course, 0. This sulfur is 1, 2, 3, 4, 5, 6. So now it's 0. Now, what if somebody decided, I want to draw mine like this, with 3 on that one? Again, this is not a resonance structure, but it is a valid Lewis structure. So let's see what happens. There we go. 2, 4, 6, 8, 10, 12, 14. Okay. So now we have, these are also all zeros. 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. So these are equally valid, really. Let's see what happens. Why don't we try to draw 3 hydrogens on the sulfur? Again, you don't have to do this. This is asking for resonance. I'm just trying to give you some other examples of what can happen. All right, and you can probably go, oh, that's going to be bad just by looking at it. So both of these are going to be okay. They're not resonance because the atoms moved. This one here, sulfur now has a formal charge of +2, and carbon has a formal charge of -2. So this is terrible for multiple reasons. The larger charges, and they're backwards. Carbon is less electronegative, so it should have the positive charge in the molecule if possible. Last one, SO2. Selenium has 6. And oxygen each has 6, so we've got 18 electrons. So these are all equally electronegative, or well, pretty close to it. So I'm just going to put selenium in the middle for symmetry's sake. 2, 4, 6, 8, 10, 12, 14, 16. Not going to work very well. Oh, I need 18, sorry. 18. Okay, so one of these oxygens is going to need to share. All right, so this oxygen has a charge of -1. This selenium has now +1. And then this oxygen is 0. Okay, let's see if we can fix it a little bit better. What if we said instead to go 2, 4, 6, 8, 10, 12, 14, 16, and let's put an extra pair, because again, selenium, as you know, is in the 3rd row, so it can take an expanded octet. So let's try that. When we do that, this oxygen is 0, this oxygen is 0, and then this selenium, 1, 2, 3, 4, 5, 6, is also 0. So it may not be completely obvious, you know, on what you can possibly do, but remember you can expand those octets. And then I guess our last option is moving this double bond over to the other side. We'll keep with our symmetry there, and so this is +1, -1, and 0. So this is the preferred configuration.